Okay, because I missed 6 and the extension's not too hard, we're going to go through this. Essentially, they just want us to describe the transformations here. These are both y transformations. How can I tell? Because they're outside the sign area. Anything past the word sign is an x transformation, except when we see a plus at the end. Those are both y. So when we talk about y transformations, we use the word vertical. So this means there's a vertical stretch by a factor of 4. Why is it a stretch? Because it's above 1. Anything below 1 would be a compression, but it's above 1, so this is a stretch. And there's a vertical translation 3 up. So that's just because it's plus 3. So that's how we would describe that. Then they want us to graph it. Essentially, we would take our normal sign points, 0, 0, pi over 2, 1, pi, 0, 3 pi over 2, minus 1, and 2 pi, and we would multiply those all by 4. So when I multiply by 4, I get 2 pi, 4, yeah, 4 pi, 4 divided by 2 becomes 2, so it becomes 6 pi, 8. And then when I add 3 to each of them, we've got to add it in terms of, actually, I accidentally changed all the x's. I'm sorry. So let's put them back. There we go. So when I multiply by this 4 and add 3, I get that. Multiply this by 4 and add 3, I get that. Multiply this by 4 and add 3, I get that. Multiply this by 4, I get minus 4 plus 3 is minus 1. Multiply this by 2 pi, 0 by 4 and add 3, I get that. So then you just can map that, and you'll notice that the period is still the same because the x transformations haven't changed. It just goes up much higher and much lower, and the new axis is at y is equal to 3. But that's how you would instantly be able to graph it by hand if you had to. Just take the 5 original points and apply the transformations. This one's interesting because it has both an x and a y. It's clear it has an x because it's right here beside x inside brackets, but it has a y, a little mysterious y, minus 1. So that minus 1 means there's a reflection in the x-axis because all my y values would change to negative. And then instead of that being a compression by a factor of a quarter, we have to reverse everything to x. So that is actually a stretch, a horizontal stretch, because we're talking about x now, by a factor of 4. Which means you multiply all your y values by minus 1, and you multiply all your x values by 4. So let's look at that. So we're talking about the main points again. We'll multiply that by 4 here, we get 0. We'll multiply it by minus 1, we get 0. We multiply this point by 4, we get 4 pi over 2, which is 2 pi. We multiply this by minus 1, we get minus 1. So we can see this sine curve goes down instead of up. Then we look at this point, pi, 0. We multiply this by 4, we get 4 pi. We multiply this by minus 1, we get 0. Then we get the 3 pi over 2, minus 1. If we multiply this by minus 1, we get 1. It's finally going up now. We multiply this by 4, we get 6 pi. And then the last one, which is 2 pi, we multiply that by 4, we get 8 pi. And we take the 0 multiplied by minus 1, and that's what we get. Notice that the period is now 8 pi. It goes from 0 all the way to 8 pi. That's because the normal period of 2 pi got multiplied by 4. Nothing else changed for that, just a period stretch. And this, instead of going up, now goes down. So if this was a normal sine curve here, this new one is much longer, 4 times as long. That's just twice as long. And goes down first. Instead, it goes down first, all the way down to minus 1. So the amplitude hasn't changed, it's just been reflected. This one has an x and a y as well. All the x values are not translated to the left. We have to do the opposite. They're translated to the right. Let's start with the y transformations. There's only a vertical translation down by 1. And then the x values, there's a horizontal translation to the right, not to the left, by pi. Which means We subtract 1 from all y values, and we add pi to all x values. If we look at our standard things, and we start with 0, 0, we subtract 1 from the y, and we add pi to it. That means we start at pi, comma, minus 1. By the way, the new axis is at y is equal to minus 1. If we look at the next value, which is pi over 2, comma, 1, and we subtract 1 from the y, we get 0. We add pi to this. Pi over 2 plus 2 pi over 2 is 3 pi over 2. If we look at the next point, which is pi, comma, 0, and we subtract 1 from it, we can see, okay, the midline is all minus 1 now. If we add pi to this, we get 2 pi. If we look at 3 pi over 2, comma, minus 1, and we subtract 1 from it, we get minus 2. So finally it's going down. And if we add pi to this, it's 2 pi over 2, which is 5 pi over 2. Then finally to 2 pi, if we add pi to it, we get 3 pi. And it ends at 0 if we subtract 1. There. Now you have 5 major spots that you can plot. And all that's happened to this sine curve is it's moved to the right by pi, and it's gone down 1. And now the last one. Has all x transformations. There's no y transformations here. So if we look at it, the big point here is it's not factored correctly. You're going to get the stretch right, but you're going to get the horizontal translation incorrect. That's because you shouldn't have 4 beside the x inside the bracket like this. So that means we have to divide everything by 4. Another way to look at that to make it easy for this fraction is you have to multiply everything by a quarter. If I multiply this by a quarter, the 4 disappears. But you're still factoring out 4. And if I multiply this by a quarter, this is why it's easy to see. I can see that this becomes 12. 2 pi over 12, which simplifies to pi over 6. And that's the actual transformation. If in doubt, take 2/3 and divide it by 4, which is what we're doing. And it's 4 over 1. A fraction divided by a fraction means we simply multiply it by its reverse, which is why I said multiply by a quarter. And you get 2 pi over 12, which is pi over 6. Okay, so let's look at how that should actually be written then. Remember, it translates to 2 pi over 12, but that simplifies to pi over 6. Which means all my x values don't get stretched by a factor of 4, but they get compressed by 4, a quarter, essentially. And then you have to subtract pi over 6. So that means multiply all your x values by a quarter, and then subtract pi over 6. So if we start here at 0, 0, multiply by a quarter, I get nothing. Subtract pi over 6, that's where we start. Nothing happens to the y values. The next point was pi over 2, 1. If I multiply that by a quarter, I get pi over 8. So you can see everything's been compressed by 4. And then if I subtract, here's the tough part, I have to subtract pi over 6, which means I have to find a common value for them both, which is 24. And I get minus pi over 24. And nothing happens to the y values. I think that's right anyway. The next value is pi, 0. If I multiply that by a quarter, I get pi over 4. And then if I subtract pi over 6, I have to do the same thing. I have to find a value in common, which is 12. And I get pi over 12. Actually, should do this one again just to get in case. So it's pi over 2, which gets multiplied by 4, which is pi over 8, minus pi over 6, which is 4 pi over 24, over 3 pi over 24, which is minus pi over 24. Got it right. And this next point, which is 3 pi over 2, minus 1. If I multiply that by a quarter, I get 3 pi over 8. And then again, I have to subtract pi over 6, which is the same as 4 pi over 24 and 9 pi over 24, which is 5 pi over 24. comma minus 1. I might have gotten some of these multiplication wrong, but that's what you do anyways. If I do the last point, which is 2 pi comma 0, and I multiply that by a quarter, I get 2 pi over 4, which is pi over 2. And then if I subtract pi over 6, I have to put them both over, I have to multiply this by 3 to put it over 6, and I get 2 pi over 6 comma 0. And that's it. Now notice it's all gotten compressed by a factor of 8. It's hard to see because you're subtracting pi over 6, but that's the method you should apply. Now, some of my subtractions and multiplications might have been wrong in that one. You can always confirm with Desmos. I'm just getting a little bit lazy because this question is pretty straightforward. Now, this last one, it helps to understand. If these are always hard because what's going on. But they say the graph shows the distance from a light pole, a pole with a light on it, to a car that's racing around the circular track. Okay, let's put the circular track. Here's the car around the circular track. Now I'm going to put a little square, little shape where the pole is. And it's quite clear that when the car is here, it's very close, the closest to this pole, isn't it? Then it's going away from the pole, and that's the furthest it is from the pole. And then it starts coming back, and now it's the closest to the pole. Then it's going again, going back. And that's what they mean. So if we represent the distance, if this line here represents the pole, the car is 100 meters from the pole when it's at the closest, right here. Right here's 100 meters. And then as it gets the furthest point over here, 40 seconds later, it's 700 meters. So it goes from 100 meters away to 700 meters, which tells me that this circle, if it goes from 100 to 700, has a diameter of 600 and a radius, which is mostly related to the things we're dealing with, a radius of 300. That's going to be very important. We can also say, okay, that can be determined right here. If we draw a line right here at 400 is the axis of this thing, we can see that it's 300 this way and 300 that way, which is an amplitude of 300, and amplitude and radius are the same thing. We can also see that it's closest to the pole here, goes up, comes down, and is closest to the pole here. Right here, that looks a lot like a coast curve, except coast curves usually start up top and come down like a bird and go back up. So it looks like a flip coast curve, probably the best one we can use to measure it. We can also see the period from that, the lowest point to the lowest point, is 80 seconds, which means we have to turn 2 pi into 80 seconds somehow. Let's go through the questions. Determine the distance from the light pole to the edge of the track. Well, that's the closest spot, 100. Determine the distance from the light pole to the center of the track. That would be right here. And to do that, we have to say the furthest 2 points and take an average. 700 plus 100 divided by 2. That's 800 divided by 2, which is 400. And that's how you determine the axis. 400 to the center. Determine the radius of the track. Well, we did that, 300. Determine the time that the car needs to complete one lap of the track. That's going to be from the bottom of any curve, sine curve or coast curve, to the bottom. But you can also do the bottom to the top and multiply it by 2. We can see there's 40. If they only had given you this portion of the graph, you could say, oh, there's 40 seconds between half the curve. So 80 seconds to complete the whole curve. Determine the speed of the car in meters per second. Okay, well, if you look at it, we'd have to figure out how round this track is and divide it by 80. The perimeter of any circle is this. It's 2 pi times r. R in this case is 300 meters. So we got 600 pi. So 600 pi is how many radians it takes. And since we're talking meters, we'd multiply that by this pi by 600. And then it does in 80 seconds. Well, let's cancel out some of the things. 0, 0. Both divided by 2, 34. Both divided by 2, 2, 15. So if we were to put it in terms of pi, it's 15 pi, 15 over 2 pi meters per second. But that doesn't really help us too much. So we would actually just take the 15 and we would divide it by 2. And we'd multiply it by pi. And we'd get this meters per second. Round up to this, let's say. To make sure that's right, let's multiply that by 80 and see what we get. We get this. That should be the perimeter of the track. That should be the perimeter of the track. Let's see if it is. That should be the equivalent of taking 2 pi and multiplying it by 300. Let's see if that is. And sure enough, it is. So you can see that you got it right. So that is indeed the meters per second, and that's meters per second in pies, which is kind of useless. We never say, my car can go 15 over 2 pi meters per second. Now, the last thing that they didn't add, which I find interesting, is we can model this. Since this is an upside-down cos curve, that would mean a reflection in the y-axis. So we would put a minus up here. Since the amplitude goes, since the axis is 400, we can put a 400 here. Since the amplitude is 300, we can put a 300 here. The only thing is, how do I change? And since it starts at 0, exactly as a cos curve would start, I don't have to translate it right or left. But how do we turn 2 pi into 80? Quite simply, we divide by 2 pi and multiply by 80. If I look at this as the fraction I'm working with, 80 over 2 pi, 2 goes into 80 4 times, which means the fraction I'm working with is 40 over pi. However, the thing in front of x is flipped always. So this is the fraction I should put in front of my x value to convert it from a 2 pi radius to an 80 pi radius. There you go. Let's make sure we got that right. So what I'm going to do is pull up Desmos, and I'm going to put f of x is equal to minus 300 cos pi over 40x plus 400. And I'm going to bring it over here, and I'm going to change the visuals. I'm going to make my x-axis go from 0 to, let's say, 90, and my y-axis from 0 to 800. And here we see it. Here we have a car that's 100 meters away from the light post, 700 meters away at 700 seconds, and 100 meters away at this, with an axis at y is equal to 400. And we can see that's exactly the graph. So if I put my y values here as 10 or 20, and here as 100, we can see that's exactly the graph that they've given us with this car. Just theirs is squished a bit. So there you go. I've taken a cos curve, I flipped it upside down. If I wanted to take a sine curve, I could. I can just throw a sine curve in there. However, notice it's no longer starting where I want it to be. So I'm going to have to take this pi over 40 out of there. And I'm going to have to adjust my curve. I have to put a bracket here so it doesn't get, there we go. Now I'm going to have to push my curve to the left or to the right to get it to start where I want it to by a quarter period. A quarter period is 20 seconds now that we're in an 80-second period. And you notice that it's not flipped correctly. So there, I would just take a non-translated y curve and move it to the right by 20. Or I could take a flip sine curve and move it to the left by 20. And get the same thing. So you can see sometimes it's easier not to use a negative here. So I can just get rid of the negative and stick with this. So this is the easiest sine curve to represent the graph. But obviously they've given it us all almost exactly as a cos curve. So why bother? I can skip the horizontal translation. I can just put a negative here and use a cos curve. And get the exact track I want. All sine curves are cos curves out of phase by a quarter period. And in this case, the period is 80 seconds, so a quarter period is 20 seconds. There's the extension.